In this question, we're going to graph the curve y equals 1 over x squared minus 4x minus 5. Well, first thing we'll do is figure out where the intercepts are. When x equals 0, y equals negative 1/5. When y equals 0, well, actually that's impossible, so there's no x-intercept. We're going to have a horizontal asymptote at y equals 0 because we've got degree 0 over degree 2. We're going to have a vertical asymptote wherever that denominator equals 0 because the numerator never equals 0. So when x squared minus 4x minus 5 is 0, we see x is either negative 1 or positive 5. So those are going to be our vertical asymptotes. Now let's do some derivative work. Y is equal to x squared minus 4x minus 5 to the exponent negative 1. So we can determine the derivative using the chain rule, and we can re-express it in fraction form. Now, if the first derivative equals 0, that means the numerator equals 0, which would mean that x is equal to 2. If the derivative is undefined, that means the denominator equals 0, which means x is negative 1 or 5. But that doesn't surprise us because we have vertical asymptotes there, so naturally the first derivative will be undefined. Now, since the first derivative is this quantity here, the second derivative can be determined using the quotient rule. Now, when you use the quotient rule, you might notice you get this quantity here and this quantity here, and we're able to factor out x squared minus 4x minus 5. Doing that leaves us with x squared minus 4x minus 5 times negative 2 minus negative 2x plus 4 times 2 times 2x minus 4. And then we see that x squared minus 4x minus 5 is a factor of the numerator and denominator, so we can have a denominator of degree 3 now and just focus on this factor. And when we expand and collect like terms, we see that we get a numerator of 6 times x squared minus 4x plus 7 over x plus 1 cubed times x minus 5 cubed, because since x squared minus 4x minus 5 is x plus 1 times x minus 5, then x squared minus 4x minus 5 quantity cubed will be x plus 1 cubed times x minus 5 cubed. Well, the second derivative will be undefined whenever x is negative 1 or x is 5, which again doesn't surprise us because there's a vertical asymptote there. The second derivative will equal 0 whenever x squared minus 4x plus 7 equals 0. But we see using the quadratic formula that that never happens because we have a negative sign under the square root. So that means x squared minus 4x plus 7 is either always positive or always negative. Well, we can see it's going to be always positive. We can sub in any real number to determine, if we sub in an x value of 0, we see 7 is greater than 0. So since it's true at x equals, since the expression is positive when x equals 0, that means the expression is positive for all real numbers because it's a polynomial that never equals 0. So it's always positive. Now, to recap, our first derivative is negative 2 times x minus 2 over this quantity here, and our second derivative is given by this. Well, we set up our intervals for our first derivative and second derivative and stack them as so. And we see that when x is a number to the left of negative 1, this quantity is positive. And when x is a number in between negative 1 and 2, this quantity is positive. Between 2 and 5, this quantity will be negative, and beyond 5 to the right, that quantity will be negative. Looking at our second derivative, we see that when x is less than negative 1, the quantity is positive. When x is between negative 1 and 5, this quantity is negative. And when x is greater than 5, this quantity is positive. So we have important numbers here at negative 1, 2, and 5. But negative 1 and 5 don't have points associated with them because they're vertical asymptotes. But at x equals 2, we have a y-coordinate of negative 1/9. Now, we know it's a maximum point because we're going from increasing to decreasing, but we also know it's a maximum point because it has a first derivative equal to 0, and it's in a concave down region. In other words, a region where the second derivative is negative. That tells us it's a maximum. So in summary, we have a y-intercept here, no x-intercept, a couple of vertical asymptotes, a horizontal asymptote, a maximum point, and we have all of this to consider. So we're going to do our best to graph. Well, we have indicated the point where we have 0, negative 1/5, right there. That's our intercept. We have no x-intercept. Our point of 2, negative 1/9 is right there. And we see that we are going to be in the region between -1 and 5. We're always concave down, and we're going to be increasing and then decreasing. So our curve is going to look something like this. Now, it's hard to draw that with a thick magic marker and not have it look like a horizontal line, but this is increasing up until this point, and it's decreasing beyond there. Now, we need to be increasing and concave up to the left of an x value of -1, but also the horizontal x-axis is a horizontal asymptote. So that means we're going to be above the x-axis, and we're going to have a curve that looks like this, where this horizontal line is being treated as an asymptote. I perhaps could have drawn that a little bit better. And similarly here, we're going to have a curve that looks something like this. And again, this is going to go into that horizontal line. Now, if you want another way of looking at that, what you can do is you can pick a sufficiently large value for x, let x be 100. And if you let x be 100, you'll see that 1 over 100 squared minus 4 times 100 minus 5 is a positive number. So it's a number that's just barely bigger than 0, but it's positive, letting you know that we're approaching from above. And similarly, if you let x be a negative number, sufficiently large magnitude such as -100, you'll see that we get a positive value for y, and so we are approaching as we go to the left from above.